Okay, hi guys. Let me just start straight. Yeah, my name is Olayinka Peter, and I'm a machine learning engineer and instructor at Semicolon Africa. I also help organize GDG Lagos, and so like I like to do a lot of machine learning in my free time. So so I do work too. And then I try to write on coffeewithpeter.com about stuff I learn along the journey. Right. So it's really exciting to once again do a session about machine learning with GDG Nairobi. The first time was in 2018. It was really exciting. I think I'm good a bit because I was really sweaty then. Okay. I must say thank you so much to Ngesa, Marvin, to Tabitha, to Irene, to I forgot the name. To the rest of the team, really thank you. I'm really honored, about this opportunity. So today we're going to look into a code lab, two code labs actually, about transfer learning with TensorFlow. And then I prepared this short slide to just talk to you guys about what transfer learning is and stuff, right? So a short slide, and then we're going to compare two code labs. So the first code lab is basic image classification using convolutional neural networks in TensorFlow, and the second code lab is transfer learning. So we're going to utilize two pre-trained models that are available in TensorFlow Hub, right? So TensorFlow Hub, which I'll show you guys as soon as it comments, is an hub with an entire directory of pre-trained models that you can easily plug into your TensorFlow code and use to train your data set and stuff. So we're going to check these two code labs, and then we're going to compare the accuracy rate, the loss rate, between both of them, and see which one proves something better, right? So let's go. So this is title: Transfer Learning TensorFlow using Powerful Models. So I felt to first ask the question, why TensorFlow? Because a number of us think there's a number of other machine learning libraries out there that do cool stuff, right? So why TensorFlow? And from my little experience, I realized that apart from the fact that TensorFlow offers excellent functionalities, TensorFlow comes with these amazing services and high-level operations that allows you to perform complex tasks and complex computations. So the beautiful thing is TensorFlow was built to be production ready, and applying every single option that they give you, right? So there's a lot, right? So TensorFlow Hub, for example, allows you to pick pre-trained models and just plug them into your TensorFlow code for your data set, and then there's a large range of serving your TensorFlow models when you're done, right? And this feels cool. This shows how that the people who built TensorFlow and are supporting it and are still maintaining it in this sense of production readiness. And then this makes scalability and easy go, right? And a great example of how easy it is to use. A great example of TensorFlow being production ready is how easy it is to use powerful models in TensorFlow. This technique in machine learning is called transfer learning, right? And then I tried to extract this definition of what transfer learning is from Joshua Benjo and Goodfellow's book, Deep Learning. right? And they define transfer learning and domain adaptation to refer to a situation where what has been learned in one setting, that is some distribution P1, is exploited to improve generalization, to improve classification, to improve to improve generalization in the sense of what machine learning is trying to achieve in another setting, say some distribution P2, right? So, in other words, transfer learning is a technique where a model which has already been trained on one problem is used in some way on a second related problem, right? And the advantages of transfer learning are numerous. So, think about transfer learning as a situation where there's this old wise man, right, and there's this young dude, and then there's this machine that can allow the old wise man to transfer his wisdom and his knowledge and all of his understanding and his experiences into the brain of the young dude, right? And then the young dude all of a sudden becomes, smarter, wiser, is able to make better decisions and stuff, right? That's really comparable to how transfer learning works, right? So the advantages are numerous. One of the facts is that learning a new task relies on previously learned tasks. So for instance, if a pre-trained model has already learned how to identify objects in images, and then you apply that pre-trained model to help you identify types of apples or types of citrus fruits, because of the fact that it already identifies other objects, it's able to easily see which object is not even a citrus fruit at all, and then easily detect citrus fruits. I don't know if you get the gist here. So, and then another advantage is the fact that less training data is needed, hence learning process is faster, right? And then a third advantage is the fact that learning gets to be more accurate, right? So our Codelab will cover transfer learning for image classification using several pre-trained powerful deep learning models built by researchers in the past. So we're going to use MobileNet and Inception. You're not using ResNet. You can easily go ahead to use ResNet and know about that, guys. So, but I'd like a short time to include MobileNet and Inception. So quite interestingly, TensorFlow X comes with a lot of these pre-trained models to be easily plugged into your code and utilized, and this came with TensorFlow Hub, right? And so I already explained what TensorFlow Hub is. Think about TensorFlow as an hub for pre-trained models that you can just pick and apply to new data sets. And so let's look at it. So let's give some time to load. Yeah, here we go. So TensorFlow Hub is a library for using machine learning modules, right? And the idea of TensorFlow Hub is transfer learning, right? Where you get to train a model with a small data set to get to be able to improve generalization in some P2 setting and also speeding up training, right? So you can see a sample of how you embed what's it called? A pre-trained model from TensorFlow Hub, and then embed it as a class layer and apply it to another another sample, right? So cool. So we can just easily browse modules on tf-hub.dev. Okay. So since we're trying to work on image classification today, we just check these guys out. So there are a number of options for both image, text, and video intelligence. Right. So if I try to check through the directory of image classification options or image computer vision options, you can see a number of collections, and you can see actual actual pre-trained models here. So this is a feature vector. Number of other feature vectors. This is Inception and ResNet version 2. So ResNet is a pre-trained model. Inception is another pre-trained model, and this is sort of like an hybrid of both of them, right? There's Inception, there's there's a large repository of different picture models that you might want to get your hands dirty with. But then I think for today we'll check MobileNet version 2 and Inception version 3, both for classification. Right, so let's just exit here and go back to our slides. Right, so that looks cool. And so to commence, we'll just jump straight into the first code lab. So you might want to sort of like type this in your browser and check it out. So I'll just quickly sort of like run through the lab. I won't be starting to explain everything, but I'll just quickly run through. Right. You can check it out. It's so both code labs. Let me open up the second one. Both code labs were authored by TensorFlow. Were written by TensorFlow authors, right? So what I just did was made a few edits and stuff, right? And then the second one is. So the first one is image classification with normal convolutional neural networks, and the second one is image classification with transfer learning with MobileNet and Inception. No ResNet. Only MobileNet and Inception. So we just open those two down. Let me take this one. Let me make some come before the second one. So this is the first one. Save this submit right now. We'll be sending image classification with image data generator. Oh yeah, so I included image data generator because of the fact that we utilized the image data generator class in TensorFlow to help organize the flow of our image directory, and also help resize and apply some transformations to our images. So to sort of like avoid overfitting, what we're going to do in this code lab is sort of like be interesting. So I didn't know if you guys have learned about image transformation to sort of like make your images increase by the number, and at the same time increase and take different dimensions. So you're not just actually making exact copies of an image, you're making different transformations of the exact image, and so you're sort of like increasing the length of the images and increasing the number of possible features for the trained network, right? Excellent stuff. And we'll then see how all of this pre-processing, all of this amazing pre-processing that we're doing with the image data to help improve our accuracy is going to affect. We're going to try to look at the effect of this in training the convolutional neural network here, and still compare that accuracy with the accuracy we're going to get from the other code lab, which is with transfer learning, right? So let's just get started. I'll just quickly run through this. Get the import TensorFlow, download data from this guy. So the dataset contains images of 5 types of flowers. So we're working with flower data sets, right? Images of 5 types of flowers: 1 rose, 2 daisy, dandelion, sunflowers, and tulips. So we create a list of those for the purpose of our labeling, right? And then we sort of like write them into folders, and so the other folders make directories of those folders, right? And then this is the part. This part is called data augmentation. So this is where we perform the transformation. So with the image data generator, I already explained that we perform randomization of 40 degrees. Sorry, we perform rotation of 40 degrees, and then a zoom of up to 50%, and horizontal flip, and a read shift as well. So yeah, then we see the flip from directory. So I already mentioned that the image data generator allows us to appropriately create the flow for the network layers, appropriately create the flow for the data into the network, right? To enable is sort of like easy training. So all of the pre-processing that we would have done normally, sort of like manually, image data generator helps do all of that, right? So we sort of like declare the batch size and the image size, and then we apply all of the transformations to the training directory. Yeah, and then so to try to write this function to show us what an image looks like after transformation, right? A single image, what does it look like? Right. So this is a single sunflower right now. This is some sort of flip. Maybe this looks like horizontal, but this is like a vertical flip. This looks like some sort of rotation. This looks like some stuff. I mean, different transformations, right? So something like do a flip from directory for the variation data too, but we do not transform, right? We just apply image data generator to help pre-process that data, and then we just create the convolutional neural network here, where we use 4 basic convolutional networks. So this is 4 convolutional networks with an output or a maximum output for each of the with the maximum output. So for one layer, when convolution is performed, there's a max pooling, and then goes into another layer, there's another max pooling, goes to another layer, there's a max pooling, and then there's a final layer that flattens it before it gets to a dense layer. And so there's value that's performed on that dense layer, and value is sort of like turns zeros to ones. So there's no negative in value. So all negative features all negative features are sort of like turned to 0 and 1. So that's what happens in value. Yeah, and then this final dense layer, because of the fact that our labels are five different types of flowers. So we ideally ask the final layer to be a 5 output dense layer, right? So, and then we compile the model. I don't know if I've pressed this already. Have I done this? I think I had. And then we compile the model. We ask the train for 20 epochs. Yeah. So I'm doing 20 epochs because okay. Let me do 30, right? Just so we get a better accuracy. Let me do 30. Let's do 30. Right. So 30. So epoch sort of signifies the number of time the cycle through that data set, through that data set happens. So for each batch size, which is sort of like a batch of the directory from the train data, how many times does the model go? How many times does that cycle happen? That cycle of training through that batch size happen? So it's happen 30 times for each batch size. So. And as soon as it's done, so this is just 2, right? I'm waiting to 30. As soon as it's done, 1, 2. So I'll just play them down. Oh, this is the final one. So as soon as I'm done, we just need to see the accuracy. So before that is completed, let's check the Semicolon Codelab and look at the difference between that one of normal convolutional networks and this one of transfer learning, right? So first we talk about transfer TensorFlow Hub, which I showed you guys what it is, which is an online repository of already trained TensorFlow models that you can use. Basically, old models, old pretend models, right? So first start with the import TensorFlow, import NumPy, matplotlib, and Keras, import login for bugs, for errors, login errors, and then. I should mention that so we could also use the option of getting the data sets from TensorFlow data sets. So we could use TechJS, and I forgot to mention that we imported TensorFlow data set as well. So this same flower data set is also available in TensorFlow data set, and so we just specify that, oh look, get us that same flower data set and split it into validation and training, and let's work with it, right? So it's the same flower data set, and then we try to print it to show us what's the total number, right? And this is equivalent to the same number in the previous code lab, right? Then we ask it to show us the size. because we want to confirm that the images are not the same size. And the reason for this is the fact that, so for our first pre-trained model that we're using, which is MobileNet, MobileNet requires that an image size should be an image size should be 224 by 224, right? So as you can see here, 224 by 224, and then normalizes it by itself. So we want to show these sizes to show how that the different images are of different shapes, right? So we want to sort of like format them, transform them into the required shape for MobileNet. And now we create a feature extractor. So a feature extractor in transfer learning in TensorFlow is a concept that allows us to understand what we are trying to do. So basically, in transfer learning, what you're trying to really do is not take the entire model, right? It's take the features of that model. Give me the learned features of that model. Give those features to me, and let me apply them to my new data set, right? And so we use a feature extractor and transform it into a class layer, and then so we get the model and transform it into a class layer which holds all of the features from that pre-trained model, and then we put it in a new model and add a final layer to it that now holds the labels of our data set, of our own data set. So look at this guy that calls the URL, put it in a class layer object that belongs to the orb, the TensorFlow orb object that we first created from the import, right? And then yeah, we sort of like have to freeze the pre-trained model, and this is because of the fact that we don't want the pre-trained model to train again, right? You don't want to train. You're not training anything from that model. It's already trained. It's got it's already trained, right? So you just freeze that particular layer. This is already a layer with the input shape that we require, and we add that layer to. So I've called this model underscore MobileNet because this model belongs to this model is the one that encompasses the our feature extractor for the MobileNet pre-trained model, and then we add the final dense layer which passes in the argument, the parameter of the number of our classes, which is 5, right? And then this is the only one that has been trained. This is the only layer that has been trained right here because we already freeze this guy, right? So this is what the summary looks like. Now we train the model for 6 epochs, right? Now compare 6 epochs to 30 epochs from the other guy, right? Yeah, let's compare 6 epochs to 8 epochs, and let's see the difference, right? And then, okay, let's check where this guy has gotten to. Oh, still at 17. So what do we do while waiting? What do we do while waiting? We're still at 17. This guy is almost done. This guy is at 3. We're using Google's almighty TPUs, right? Yeah, so let's just wait. Let's just wait. So while we wait, I should probably remind you guys to wash your hands. Yeah, keep washing your hands until, right? Keep washing your hands. Okay, so this is almost done. This dude is done. Right, so we can plot the accuracy from our MobileNet model and look at what we've got. Look at what we've got. So if I use a ruler to trace this guy, let me see. It's a little bit above 0.90. So I can call it 0.9. 0.90, It's a little bit above 0.90, but then let's just say 0.90 then. Let's say 0.9. Okay. I feel like I should add a few units to that, but then. So I'm looking at the validation accuracy. I mean, validation accuracy is more significant. It's more important, right? Because I mean, if you've got your training accuracy way high and then validation accuracy is low, that means that your model is doing good on your training data set, but it's not doing good on your validation data sets. And so that's overfitting, right? Which is a really bad case, and so you sort of like have to do some work with your data set again and start over again. And so this is for the training validation accuracy, while this is for the loss, and it looks similar. Loss is usually supposed to reduce to minimum 0, right? 0.2 for training loss looks good. 0.2 validation loss at 0.3 looks good. And now we can sort of like check the predictions. Right, so we just put a class name there. Let's predict what. So this is a comparison of the predicted batch and then the predicted class name. So we took that a particular batch of validation images, and then of our trained batches. So we took a small batch from our train batches, and we took the labels, the actual labels of those train batches, and then we asked the model of the MobileNet to predict, right, to help classify what those labels, to classify what the labels should be, and then we compare the right labels with what the model predicts it to be, and then we just this is where we now say, okay, show us what we've done, right? And this is the actual labels up here, and this is the predicted labels below. And it looks like MobileNet did a very good job. Wow, looks perfect. Looks perfect. Let's plot and see if there's any difference. So I plotted the actual images, and so if the predicted class name is equal to the actual label name, it's going to be, the color is going to be blue, but if it's incorrect, the color is going to be red. My goodness. So the first time I tried this, there were two red, right? I'm like, okay, this looks interesting. So MobileNet is performing cool, right? So we're going to do the same thing with the Inception model, right? And I already mentioned that. Oh, right. So it's an Inception model feature vector to do the same thing, and then we'll do, so instead of MobileNet this time, we're using the Inception model feature extractor to extract the features, and then add an extract layer, an extract dense layer to represent our actual layer, our actual labels, and then train that last layer on a small data set, right? On a data set, and see how this Inception model how it performs in comparison to this MobileNet model, and now how they now perform in comparison to this guy that is still running. Let's check. It's almost on 30. Okay, should we complete it then? Maybe we should just complete this dude. It's already done. Okay, this guy is already done. So I think, yes. Oh, this looks, yeah, but I mean, so imagine that we had to do 5 different transformations, right? We had to do 5 different transformations for each of the images, so just so we could expand the possibilities of different features, right? In the network, and then it looks fair. But 0.7, 0.76, 77, 78. This is 0.78. 0.78 for training accuracy and 0.75 for validation accuracy compared to where are you? Compared to 0.95 and 0.90 because we use transfer learning. And look at how short the time was. Look at how I mean, compare the epochs, compare the time, because we do transfer learning, right? So that's it. That's just the power of using pre-trained models, right? I mean, right? I mean, if we wanted to improve, if we wanted to optimize and try to get as much as and try to get an optimization that can improve accuracy to some larger value, right? Would we get to 0.9? How much would you have to tweak? How much would you have to increase this? How much would you have to, and then we did not do any transformation on this same exact here, right? So the point is the power of reasoning models is really amazing, right? So let's just go ahead and check for the inception and see. As oh no, I didn't. Sorry, I should have clicked this guy first. I mean, I usually call it play and pause instead of run. I call it play and pause. So play and stop instead of run. I should have run that surface, but I should have played that surface because the icon looks like play, Yeah. So this is us compiling the model and assigning the epoch number to 6 and then asking it to fit this begin training, right? So we're going to wait for the cycle to get to 6 as well. So I'm done with this guy. I'm going to wait for the cycle to get to 6. In case you've forgotten the links, this is the first link and this is the second link, right? This is the first link and it's the second link of both of the labs. Right, and yup. So this is that. So while we're waiting, I probably should tell a joke, but I don't know jokes. So let us wait in silence. We just wait in silence. Also, by the way, I should spill this, but then I don't want to because I should spill the fact that the actual call, which was a live call, right, which was a live event, didn't go so well because there were some audio issues. So I mean, huge thank you to the organizers that they gave me an opportunity to record another one with better audio, right? So if you were in the live event and I mean I felt the audio wasn't well, and at some point I still don't even know what I was saying because I mean people were complaining about the audio and then I wasn't doing so well. I felt I was mumbling words together. I didn't really explain what the code looked like, Yeah, so this is another chance to get this done with. Okay, so while we are still waiting, this is so we're almost at 5. While we're still waiting, maybe we should check some other modules, some other project modules. Okay, so yes, I should mention that. I mean, it's pretty easy to add a third ResNet model. So if you wanted to do ResNet, if you wanted to do any other project model, I mean, you just look for the URL in tf.dev and apply it to Feature Extractor. I mean, the idea is you understand that okay, the concept here is feature extraction because we're collecting a feature vector. Alright, so oh yes, I forgot to mention that the image resolution for Inception is 299 compared to 224 of MobileNet. Right, so yeah. So we are almost done. Yeah, and immediately after that's done, I want to check the accuracy and compare to MobileNet's accuracy. Right. Those plots are running. So this looks like some 0.93 or 0.94. 0.93 or 0.94. 0.935 or 0.94. Am I wrong? But then validation is at, let me use, you can call validation at 0.90. Let's compare with MobileNet. I think I've forgotten. Wow. So apparently MobileNet does better than Inception, of which when I ran this some 2 days back, Inception did better. I mean, I'm wondering why MobileNet is performing better. So really, MobileNet is sort of like an improvement, right? But then that's not something I want to argue about, because more times I've tried in the past, Inception has proved a little bit better than MobileNet. But then let's see what the prediction will look like. I mean, we've not even compared the loss. Sorry, we don't even compare the loss. This is 0. Less than 0.2. This is 0.3 and was 0.2. I think that the loss accuracy for, I mean, they look very similar, but then the loss accuracy for Inception model looks better. So then let's see. I mean, MobileNet predicted all of our batches correctly. Let's see if this dude right here will do the same. Please don't fail me. Do not fail me. Do not disappoint me, please. Whoa, it seems to do pretty well too. Whoa! Yeah, so both the MobileNet portrait model and Inception model performed really amazing, right? This just looks like the first time both of them would not get a prediction wrong. So with this, we've come to the end of this session. Thank you for having me. My name is Olayinka Peter, and you can follow me on Twitter. Thank you guys. Thank you, GDG Nairobi. Yeah, thanks guys.